Welcome all. In this video, we are going to talk about UV visible spectroscopy. So UV stands for ultraviolet region and visible stands for the visible region. Okay, normally in terms of wavelength, the UV region is divided from 200 to 400 nanometer. That is when the wavelength range corresponds to 200 to 400 nanometer, then the region is called as a UV region, and a compound which observes or emits radiation in this region is said to exhibit UV spectra. This is said to exhibit UV spectra. Okay, and this is for UV. And for visible region, the wavelength range is from 400 to 750 nanometer. Wavelength region is within 400 to 750 nanometer. Okay, when a compound observes radiation or emits radiation in this region, so then that compound is said to exhibit UV spectroscopy. Okay, how on visible spectroscopy. So 400 to 750 is visible spectroscopy, 200 to 400 is UV spectroscopy. Okay, how on the spectra occurs? So the spectra occurs due to the excitation. UV visible spectroscopy occurs due to the excitation of the electrons. So the electrons get excited from one orbital to another orbital, and the difference in energy is observed. In case of the absorption spectra, when an electron comes from higher orbital to lower orbital, the difference in energy is emitted, that is emission spectroscopy. So we have already seen there are two types of molecular orbital. In terms of molecular theory, we have seen sigma molecular orbital, sigma molecular orbitals, and a pi molecular orbital. Okay, there is another type of orbital which is called as an N, non-bonded orbital. Non-bonded orbital is nothing but the orbital which does not take place in the bonding, So that is called as an non-bonded molecular orbital. So if you take a sigma orbital, sigma is a sigma and sigma star. That is, sigma is the bonded molecular orbital, sigma star is the anti-bonding molecular orbital. Pi will be having pi and pi star. Pi is the bonding molecular orbital, pi star is the anti-bonding molecular orbital, and there will be an N which has got only one orbital, non-bonded, because it is not going to take place. It does not take place in the bonding. So there is no two orbitals, only one orbital. Okay, so in terms of the energy diagram, so if you take an energy diagram, so sigma bonding molecular orbital will be having the least energy. Sigma bonds will be, that is bonding, sigma bonding will be having the least energy, and then pi would be having an next energy, pi bonding. Okay, in terms of increasing energy, so there will be an sigma bonding molecular orbital which is having a lower energy, then pi bonding molecular orbital which will be having a little bit higher energy, and there will be an non-bonded N means non-bonded orbital. So electron may be present in the sigma, pi or N, and pi star which is having a higher energy than the N, pi star anti-bonding orbital, and will be having a sigma star anti-bonding orbital. So these are the energy diagram. So electron from the sigma can get excited to the sigma star. Okay, so this is called as a sigma star transition. So electron from sigma orbital can get excited from the sigma star orbital. Absorption, it absorbs the energy, difference in energy between the sigma and sigma star. It may get excited from sigma to pi star. It may get excited from sigma to pi star, so which is called as a sigma to pi star. We are talking about the absorption spectroscopy. So in the emission, it will be a reverse. Okay, an electron from sigma star can jump to the sigma, or from pi star can jump to the sigma, and electron from pi can go into the sigma star. Electron from the pi orbital can get excited to the sigma star orbital, so which is called as an sigma pi to sigma star, and from pi to it can go to the pi star orbital, so which is called as an pi to pi star orbital. Okay, electron from non-bonding molecular orbital can go to a sigma star orbital, which is called as an n2 sigma star, and from the n orbital the electron can go to a pi star orbital, so n2 pi star. Basically, the difference in energy between the sigma and sigma star, if it is absorbed, it goes to a sigma star. It is called as a sigma star excitation. If it is get excited from sigma to pi star, it is sigma to pi star excitation. It can be an pi to sigma star, sigma to sigma star, or n to sigma star. It is a non-bonded electron can absorb energy and go to a pi star or sigma star. So it can be n to sigma star or n to pi star. There are a few allowed transition, that is a symmetric consideration allows some of the transition. Normally transition within the same symmetry, that is from sigma to sigma star. So the allowed transition is due to the symmetric condition. The allowed transition is sigma to sigma star and pi to pi star. So sigma same symmetry, and electron from the sigma orbital can get excited to the sigma star orbital, or electron from the pi can get excited to the pi star orbital. And there is also another allowed transition, n to sigma star. It is also allowed due to symmetric condition. If the excitation occurs in the allowed region, the absorption of the energy would be more, and the molar extinction coefficient would be order of 10 to the power of more than 10,000 or more. Okay, so that is called as an allowed transition. And there are forbidden transition. So there are some forbidden transition. So forbidden transition is when it is not allowed. Between two different symmetries, the energies are not allowed. For example, if it is sigma to pi star, it is not allowed, or pi to sigma star, it is not allowed, n to pi star, it is not allowed. These are the non-allowed transition, but it may occur actually. In the nature it may occur, but when it occurs also, its molar absorption coefficient, that is absorptivity, will be very less than 10,000. So it is naturally said to be a forbidden transition. So if you consider the energy of the excitation, so sigma to sigma star would be having the highest energy, followed by sigmas to pi star, that is the energy required to get excited from sigma to sigma star would be the highest, followed by the sigma to pi star, which is followed by pi to, so it is, I think I have this is wrong. So sigma to sigma star will be the highest, and pi to sigma star will be the next highest. Then comes the n to or we can say pi to pi star. Okay, then comes the n to sigma star, and then n to pi star. So this is the order of the energy, that is sigma to sigma star will be having the highest energy. Then comes the pi to sigma star. Okay, pi to sigma star will be the having the next highest energy, and pi to pi star, and then n to sigma star, and then n to pi star. This is the order of the energy of the absorption. So with this we will end this video, and we will meet in the next video. Until then, bye.